So, as usual, I did not finish what I wanted to do last time, so we need to close the circle. But I learned that in this community, what you close is not a circle, but a petal, right? So we need to prove the second part of what we said that is necessary, that is enough in order to prove resolution singularity. So the theorem we prove is that for there's a smooth functorial resolution singularity invariant inv. In this, I'm stating it now in the language of ideals. The invariant is of the ideal, and also for every ideal on a smooth variety, a center J, such that the invariant, which exists on everything, and the center that I want to have on everything, satisfy these two conditions. The vanishing locus of the center, the support of the center, is the maximum locus of the invariant. That's what I did finish last time. And the more subtle thing that is that if you are not careful with choosing the center will not hold, is that the maximum, the invariant of the transformed ideal on the deformation to the normal cone equals the maximum invariant that you started with. It cannot be less because you already have this locus where the invariant is the same. But it could possibly be bigger, and we saw an example blowing up the origin with no weights for the Whitney umbrella. In that example, the invariant actually grows. So, and it gets worse if you're not careful. So with our choice that I described last time, inductive choice, the invariant does remain the same on the deformation to the normal cone. And we deduce from that that the maximum locus is this V. So when you remove the V, it drops. And therefore, in the blow-up, it drops. So that's what enables us to show resolution of singularities. So let's prove this. And I want to recall a couple of things from what I said. So what is the transform of the ideal I? It's what I get by pulling back all elements of the original ideal and removing as much of the exceptional as I'm allowed to remove. And we made the calculation. The amount that I am allowed to remove is s to the power L. Remember, s is the variable of the deformation. It defines the exceptional locus. And I can remove exactly L times. I'm guaranteed to be able to remove. And this is this is enough for what I need. So in order to prove this, we have to use the inductive structure of the invariant. It starts with the order of vanishing. So we'd better know the following claim. The claim says that the maximum on B of the order of I prime is still A1, is still the order of the original ideal and not more. That's one of the first things that everybody proves, Hirnaka, Villamayor, Pearson-Millman. That's quite a general property. So let's just see how to prove this. I'll make a simplifying assumption. Remember, what's the order? The order is obtained by taking A1 derivatives and seeing that you get a unit. And what I know is that the order of the ideal I is A1, and that X1, in the maximal contact, appears in that derivative. So this is truly without loss of generality, but ask me if you, let us assume that x1 to the a1 appears in some f inside I. So it's a leading, a part of the leading term of x of an element of the ideal. So this manifests that x1 is a maximal contact. So dx1 to the a1 f is 1, and dx1 to the a1 minus 1 of f is x1. So I'll assume that I've massaged my equation like that. It's not hard to either reduce to this case or prove a slightly more general statement if you prefer, so that this is that is legal to assume this. And now we just want to see what happens when we take the derivative, when we plug in here. And we already know that, so the maximum order is going to be a1. Which derivative are we going to take? And what element might be a maximal contact element? Well, the only thing that we could possibly take is the derivative with respect to x1 prime. And the maximal contact should be x1 prime. That would actually be the next claim. But let's show this. So let's apply the chain rule. So let's take the x1 prime derivative to the a1, apply to the transform. And the transform is obtained by s to the w1 x1 prime and various other things. And if I do that, I can use the chain rule. Okay, we use calculus. I know that we are algebraists, but we also are geometers. We have to use calculus. So the s does not appear here, so s to the minus l. Now I'll use the chain rule. I have the usual derivative with respect to x1 times the derivative of x1 with, so this is x1, derivative of x1 with respect to x1 prime, and I do this a1 times. So I have s to the power a1 times w1. df dx1, and then you plug in. Okay, remember L was exactly A1 times W1, A2 times W2. L was obtained as the factor that you use in order to rescale things. So this cancels out, and here you get, so this is the A1. And I assume that this is 1. Okay, so the order is A1. Okay, so what do you need to do? So we prove that the order is A1. I want to also prove that x1 prime is maximal contact. Okay, so all I need to do is to change the computation here to allow for that. So I use this. I take, so A1 minus 1 W1 times this. So what I get is, so I get s to the minus w1 times x1, which is x1 prime. Okay, so the computation is just, so all right, so it's clear that we have done things so that this should work. And this part exists already in previous works in almost the same way. But the next part was not possible because weights were not used. So the final thing, so we've shown that that the invariant starts with A1, and we need to show what the rest is, and that J is x1 prime to the A1, and we need to know what the rest is. And there we just use induction. So let's for a minute pretend that the coefficient ideal of the transform is the transform of the coefficient ideal. And then by induction, so by induction, the invariant of I prime is A1, and then the invariant of I prime is equal to x1 prime divided by the A1 minus 1 factorial. Okay, but what is this? This is the this is the invariant restricted to the vanishing locus of x1. So if H is the vanishing locus of x1, then I'll write, here's the vanishing locus of x1 prime. It's a hyperplane in each fiber. And the point is that H prime is the deformation to the normal cone of H with respect to the Jx1, Jh, or J, yeah. So now we can just apply induction, saying that the invariant, so we are in one lower dimension, the invariant of an ideal in one lower dimension when you deform to the normal cone equals the invariant of the original ideal. So these B to BK are the B2 to BK that we had before. So basically QED. Well, QED assuming the invariant of the coefficient ideal of I prime, x1 prime, equals the invariant of the coefficient ideal of I x1 transformed. And that's a little lemma that you prove by taking derivatives again. So I'll skip it for now. So all that this is to show you is that the inductive structure that we have designed enables you to prove everything and rather without effort. So the hard part is to design things so that it would work. I would like to pause here and ask if there are questions about the first petal of my lectures. Okay, I'm told that either you use the speaker or I'll repeat your question.
Okay, so how do you do the maximum of J? Like why is the maximum?
So this is what I showed before. So the question is part one. This is something that I did somewhat quickly last time, and for that I need to pull up my my notes from last time. Do I have my notes from last time? Right, so first of all, we showed that the maximum locus inside the vanishing locus of x1, that's almost the definition of maximal contact. And then we applied induction, the fact that the x1 says that by induction, the vanishing locus of the J of the coefficient ideal is the the support of the J of the coefficient ideal is the maximum locus of the invariant of the coefficient ideal, and therefore they agree. So that, again, the inductive structure of the invariant and center give you everything with a little bit of calculus. Did I answer your question? Okay. Okay. All right, so here we come to the thing, the part that I guess you are ready to pounce, the second petal. And the second petal is about the foliated aspects. So I need to write some names here. So anything I say, so new results are together with Belotto Temkin and Wlodarczyk. And I'm required to mention that there are earlier results about vector fields, and so in dimension 3, there's by Panazzolo and by McQuillan and Panazzolo. Which the audience is probably more familiar with than I am. So let me say what we are investigating and what we can prove about what we are investigating. Okay. So you all know what a foliation is, and remember that F, a foliation. So my ambient space Y is non-singular, and F is in Ty, is non-singular, is smooth, non-singular. That precisely means that it is a subbundle. So Ty on F is locally free. And it is log non-singular. So now I have Y and D is a nice SNC pair. So if the foliation is log non-singular if Ty minus log D, mod F is locally free. So it's a subbundle of the logarithmic tangent space. I want to recall something that you all know very well, that there's a fundamental difference between the two. If you have something non-singular, then the existence and uniqueness theorem says that locally in the Euclidean topology there are, you can integrate it. There's holomorphic integral. In the Euclidean topology. However, in the log non-singular, that's not quite the case. And I suspect some speaker will tell us about replacements of this. What Jarek tells us is that, so there are no holomorphic integrals, but so there are holomorphic integrals locally on B. On some B. But B is not birational to Y. So B is that is suitably chosen. So you do lose something. One thing that Belotto put in the middle is what I'll write, monomial log non-single. So log. So these are the things that locally look like spanned by which variables do xi d by xi that locally look like that, where the xi are parameters from the log structures, and the ai are constant. If you want q or c, whatever you want. So these have sort of transcendental, multi-valued integrals locally, and in that sense, they are better than general log non-singular. Is that reasonable? So we'll come back to these. I hope you don't mind that foray. So let's talk about reduction of singularities. What do I want to say about reduction of singularities? We all know that in general, a foliation cannot be resolved by a smooth foliation. It's worse than that. So Michael told us that for morphisms, morphisms can always be resolved by log smooth morphisms. But it's not true that foliations can be resolved by log smooth foliations. So almost always. The example that Guillaume wrote says that if you have something with take a vibration, a smooth vibration, blow up a point, then any further blow up, you can't get rid of the zero of the vector field that you get where you blew up. In that case, you do have a log smooth versions because of the morphism case. So there is a theorem which says that if f is birational, is algebraically integrable, then there is a log smooth resolution. So you can deduce this from resolution of morphisms, but in our paper this is part of a more general result. And one of the things I want to tell you is about the slightly more general or somewhat more general result. And there's maybe one strengthening. I'll state it. I'll state it when it comes. Time is short. So following Michael's lecture, the central idea is to work with principalization and see how much you can get away with principalization. This is a question that was raised in Belotto's thesis, and in essence, we solved that question. the point of view is now resolving subvarieties of foliated varieties. So resolution inside foliated varieties. And for the time being, I don't care about the singularities of the foliation. If I want to say something about foliations, then I'll have to restrict myself. So suppose Y is smooth, F foliation, and X inside Y is a singular subvariety, or possibly singular subvariety. And the question is, what can you say? What can one say about resolution, embedded resolution of X in Y in a way that accounts for that respects the foliation F? This is exclamation points, not factorials. So I'll give you an easy theorem. Easy because we have Hirnaka. And I'll give you a theorem that may be new. At least I think it's new, but I'm not a foliation specialist. Okay, so theorem. If X is F invariant, which just means that F of the ideal of X is inside the ideal of X, then the functorial resolution process is F invariant. No. F is an arbitrary foliation for now. So when I say so each step of the resolution process is a blow-up of an invariant center, and therefore F lifts to a foliation on the blow-up, and as you continue, you get to the transform foliation, the strict transform of X, and the strict transform of F is invariant under the transform foliation. That just so why? So this follows from factoriality. Why is that? If I have any operator in F, then I can think of X T delta as an action of C or a little piece of C on the ambient space that fixes X, and factoriality says that the whole process will be invariant under delta. So it's the whole process is invariant under every single element of X. I cannot hear you.
I'm assuming that X contains singular. I mean, I allow X to contain singular.
I'm allowing, so F invariant just means F invariant. So I'm allowing it to be in the singular locus of F. I'm allowing it to be just tangent, yeah.
Even if you get the center of your blow-up contains X.
No, the center of the blow-up in the usual resolution of singularities is going, all I'm saying is that the center in the usual resolution of singularities, in the theorem that we proved last time and finished today, is invariant under F. And the NF will lift after. Sorry, I can't hear you.
I mean, if you blow up X.
Well, the strict transform of X is well defined. I'm not resolving f, I'm resolving x. F might be singular, and its transform may be singular, and get more singular, if I'm not careful. So for now, I really don't care. You really care about resolving f. I'll get to what I can say about that.
Okay.
So this is really a direct consequence of Hironaka. If Hironaka is to be functorial. So if it's functorial under, at least, I mean, I need functoriality under many, under formal group actions, and that is also true for Hironaka. Hironaka knew that his method is functorial, by the way. He just, for some reason, he was resistant to saying the word functorial. I was at a course where a student sort of forced him to say the word functorial. That somehow stayed with me. The student wasn't me. I think it was the last student of Hironaka. Okay, so that, are you okay with that? You believe this, right? So here's another thing. So here's a theorem which I believe is different from what you assume. X is generically transverse to X. I really hope to give examples at some point in this hour. We'll see if we get there. Assume X is generically transverse to X. You know what that means? To F. It's very restrictive if X is generically transverse to X. Okay. Then there exists a sequence of F-aligned blowups of Y. So ending in, so the end result is a proper transform of X inside a proper transform of Y and a transformed foliation F. Just take the saturation of what you get away from the centers of the blowups, such that X prime is transverse to F prime. Now, is this a known result? I think not. Okay. You think about the following example. If you get bored, what happens with y cubed minus x squared equals 0, and the foliation is the foliation generated by dy. So it's generically transverse, but certainly not transverse at the origin, and think about what happens. I have to tell you what F-aligned is. So what is an aligned center? A center is aligned if it's put together from two types of center. So one type is an invariant center. So y1 to the b1, yk to the bk, where this center, so j inf, so f j inf. So a center that is invariant under the foliation. And the second is a transverse center. So this is AYL, xk to the ak, where d by dxi are elements of F. So really transverse to the foliation. And so a center is aligned if it's put together. So here's here's a generic F-aligned center. The first variables are transverse. The last variables are, at least on formal coordinates, invariant.
What's the setting of your result?
Everything is local. In fact, in order to have such a description, it's a center, so it's a monomial valuation that on formal completion looks like that, where the yi are invariant. You have to go to formal completion to see the. What's that?
So it's local.
Everything is local, but to find the variables, because you cannot integrate, basically. To find the variables, you go to the formal completion.
Do you know that if it holds globally or not? If everything is global, can you have the same statement?
The theorem is global. The center I define is an algebraic center. It's a global center. It's just that the local description is like that. That's an important point. That's one of the hardest points that we had to understand in order to do this. So let's write a combined theorem from this theorem and that theorem. So now I have to lift some things, and while I'm doing that, you can.
Sorry to go back to the previous theorem, but I can't understand it. For me, it's an empty statement. Because you are blowing up subsets of X, right? And X is already F invariant.
Yeah.
So it's strict transform is invariant, right? So what's the content of the theorem?
Yeah. So the point of the theorem is that in Hironaka's algorithm, the centers are invariant. I mean, I could make a mistake and blow up a center that is not invariant. So the fact that X is invariant doesn't mean that every subset of X is invariant, because I only know that the foliation is tangent to X. So inside X, there might be some. So here's X, which may have a singularity, and the foliation is tangent to X, but I might make a mistake and try to blow up this. What this says is that if X is invariant, then I will never do that. So it does feel like I'm doing nothing because Hironaka has done everything for us. So I'm stating that in order to be able to state a combined theorem. Yes. Yeah.
But formally it was not observed. We don't find this in literature.
So in a sense it was. So there's a paper of Kawamata which uses the infinitesimal invariance of resolution of singularities, assuming, so Kawamata wrote it in the 80s, assuming that Hironaka's algorithm is functorial, invariant under automorphisms, and he showed something about, so assuming abundance basically showed that, it showed something in minimal model program using factoriality for vector fields. So, this was in the air.
So,
Of course, things that Kawamata, I mean, you could say that Kawamata knew everything, but okay, so you want to also comment something.
So my comment is that F is just should be thought as automorphism. We are not studying singularities of F. They have nothing to do. We are not resolving them, and usually X is inside of singular locus of F. F should be thought as just automorphism.
It's a sheaf of local automorphisms of Y. And that's what that first theorem is about. The second theorem is not about that. It's something about transversality. So what's the combined theorem? The combined theorem is a resolution of Belotto's question. Let's see if this chalk is any good. So combined theorem. Oh, one really has to press, my God. So if X inside Y is a singular subvariety of a foliated variety, the foliation can be very singular again. There exists a functorial sequence of F-aligned blowups of centers like that. So, Belotto defined a line for usual smooth centers, and we extend it to weighted, arriving at X prime inside Y prime F prime, so that the subvariety is smooth, and moreover, it is, so if you want J, which is Ix, is an F prime aligned center itself. So not only the subvariety is smooth, but it behaves as well as possible with respect to the foliation. If it were invariant, it will remain invariant. If it were generically transversal, it will become transversal. And this is the combination of the two. This is, in essence, the question that Belotto solved for, in some cases, for low dimensions, or very locally in general, in his thesis.
So in here, transverse is in the sense of differential topology. Do you ask that?
This is it. This is it.
It's not transverse in the sense of differential topology.
What's transverse in the sense of?
Differential topology, you ask that the tangent space of the two objects generates the whole space.
So this is a transversality that I'm asking.
Not that.
So how do we do it? Yeah, method. Construct inv. So f inv of I, an invariant that knows about the foliation, and a center associated to the foliation and the ideal that satisfy the theorem, the criterion. So I'm not going to go into detail about it, except I want to give you an example that shows what's different. And I want to draw conclusion about reduction of singularities of foliations. I think I have enough time to do both. What do you want? To start with an example or with, okay, everybody's tired playing with an example. I mean, if I had an hour, I would choose something from one of these beautiful boards. But since I don't have an hour, let's do, I think I've used this, and I've used that, so I can erase this and So let's look at the simplest example, the example that I wrote there. So let's calculate the F order of this ideal at the origin. F order is the first time that when you apply derivations from F, you get a unit. So the usual order is the D order. Michael didn't tell you, but for the logarithmic case, we do use D log order. Okay, so what's the F order of this ideal? How many times you need to take a derivative from this foliation to get a unit? Well, you need to derive by y three times. So this is different from the order. What is the coefficient ideal? So you need to take, so what you really care is about I of y, so restricted coefficient ideal. You take the coefficient ideal and restrict. So in this case, you just take this ideal, restrict, so you get x squared. And then you have to rescale it to order 6. Okay. Now, what is the restricted foliation? Okay, I'm restrict. So it's the trivial foliation by points, because d by dy is transverse to the variable y. So there's nothing left. F is the zero foliation. So the F order of the F order of this is what? How many times do you take a derivative from this to get a unit?
Blue screen.
Infinite, right? It's infinite because you never get a unit. Yeah. Okay, so I call it infinity because you never ever get a unit. So F order is infinity. So what you do when you get to F order infinity is you take, in this case, this ideal, you take the derivatives, the F derivatives as much as you can, so this is what you have. And you take its usual order. So so F invariant of x to the 6 is infinity plus 6. You remember the infinity because F did you nothing, but usual derivatives gave you 6. And we rescaled it by 3 minus 1 factorial, which is, did I do it right? Did I do this right? 3 minus 1 factorial is 2. No, so it was not x to the 6, it was x to the 4. Right? Yeah, it was x to the 4. We rescaled it by 2, so plus 4. So we scale it by 2. So the F invariant of y cubed minus x squared is 3 comma infinity plus 4 divided by 2, which is 2. This says 10 minutes. Is that possible? I started at it. Yeah, I started it on 20. That's what I forgot. I looked at the clock and that was a mistake. Okay, so I don't have that much time. All right, so I'll finish this example. So what I do now is, of course, use the weighted blow-up of y cubed comma x squared. if I do the weighted blow up of y cubed comma x squared, I get I don't put an infinity in the j of this of x and y. So this becomes the equation. So I plug in, and after that I'll take the quotient. I plug in the and of course, so this is exceptional, and I remove the locus where x prime and y prime are 0, so that this becomes this becomes transverse to the transform of the derivative. So here's one other thing that I don't have time to explain to you. It's Jarek's observation that when you work with the deformation to the normal cone, it's easy to compute the transforms of the basic derivatives. The transforms of the transform of d by dy, the correct transform is d by dy prime. And away from the origin, it is indeed transverse. Because if y equals 0, then x equals 0. So this becomes transverse. Okay, so I want to use the last couple of minutes to say something about reduction of singularities. So that a couple of things that help us, which say that F-aligned blowups preserve nice types of foliations. So, theorem and F-aligned blowup of log smooth. F is log smooth. So smoothness is not preserved. Jarek will tell you that on the coordinate construction it is, but that's a manifestation of this theorem. And F line blow up of a monomial. F is monomial. So nice foliations are preserved by F-aligned blowups. So also the restriction of a log smooth foliation to an F-aligned center is log smooth. The restriction of a monomial foliation to an F-aligned center is monomial. So I'll define a class of foliation, a class C of foliation is thick if it is stable under smooth pullbacks. Let's say log smooth pullbacks. Aligned blowups. And restriction to aligned centers. And with that, I can state the following result. I want another small part of the same definition, I guess. So F is pre-C if there exists a morphism of dominant birational maps, dominant rational map, and a foliation G on B, such that F is phi upper star, the foliated pullback of G. So, in particular, algebraically integrable foliation is a pre-zero foliation, if you wish. Certainly, the zero foliation is. What's that? Where with G in C. Absolutely. Thank you. And then the theorem is that if C is thick, then you're welcome to change the name thick. I made it up this week. We don't have this. There are so many things in mathematics called normal or regular. Thick is used as, the French is épais. So there's a notion of courbe épais that Colliotte-Hélène introduced, I think. Anyway, if C is thick, then any pre-C, this also, please help me find a better name for this. Pre-C foliation has a C reduction, C resolution. So you have, in fact, a birational transformation such that the transform of F is in C. So in particular, if you have an algebraically integrable foliation is resolved by log smooth, 1 minute, is resolved by log smooth, a pre-monomial foliation. So there's a name for pre-monomial, it's called Darboux, I understand. So a Darboux foliation has a monomial reduction, and in fact, monomial and log smooth reduction. And I suspect that a pre-log canonical foliation has a log canonical reduction. All you need to show is that that log canonical ones are, the class of log canonical foliations is thick. And we have some idea. So certainly they are stable under transverse blowups. The subtle remaining point is to show that a log canonical foliation is stable under invariant blowup of an invariant center. I think I'm out of time.
We're more flexible than the telephone, so maybe if you need some.
Yeah, I mean, I can use another hour to give you examples. I mean, I'm not sure he's allowed to come.
So I have a comment that there was a question about transverse section. So this is a standard notion from differential geometry. There is no other transverse section.
No, I mean, it's for transverse section, but it also works for.
There are two notions, transverse and transverse section. So okay. For transverse section.
So if you have something that generically transverse section, then the blowup will be transverse in your notion.
Yeah, so this is standard notion.
But Pereira had a question also. Yes, Georgie.
So
This makes me think, can you prove, for instance, does this imply that foliation, co-dimension 1 foliations, which are pullbacks from foliations on surfaces, do you have a resolution for them? Is this easy?
So are these, so if it's a pullback from a surface, then on the surface you can get it to be elementary or whatever you call it. Yeah. And the question remains, is it true that elementary is thick? Okay, so this is something that Andre knows how to prove, but I don't. Okay. So you need to know that the aligned blow-up of an elementary foliation is elementary.
Thank you.
Oh, that's, yeah.
I want to know, we say generically transverse. Could we think in language of algebraic geometry, like it's transverse to the generic point or not?
So you're asking what it means to be generically transverse?
Yes.
It means, if you wish, this what you're saying now.
Okay, okay.
I mean, our results also work in complex analysis where there are no generic points, or there are no generic points if you don't forcefully introduce them. But okay.
Thank you.
It is sufficient if it's transverse at one point.
Oh, that's right. That's right. Yeah. If it's irreducible.
More questions? Okay, let's thank Dan again.